Hello, honors pre-calculus. Good morning, good afternoon, good evening, whatever it is, whatever time it is as you're watching this. We are going to go ahead and get started with our last chapter of the school year. So we just finished what I call chapter 10A, the conics chapter. So now we're going to look at the second half of chapter 10. So this is what we like to call chapter 10B. And this is going to be two different topics we're going to look at. This week, we're going to focus on what we call parametric equations. And next week, we're going to look at something we call polar coordinates and polar equations. So this video today is to introduce to you what parametric equations are. On our next lesson, Ms. Cronky will go ahead and go through an application of parametric equations that should feel very familiar to those of you who have taken a physics class. Okay, but right now we're just going to talk about the basics of parametric equations. I'm going to introduce to you what they are. We're going to talk about how we graph them in a couple of different ways and how they relate back to some of the graphs that we've been talking about recently and not so recently. Okay, so I'm going to go ahead and connect to my iPad here. Okay, and we're going to talk about parametric equations. Okay, so parametric equations is going to be a set of functions. So we're going to have an equation for x and we're going to have an equation for y, and they are going to be in terms of a third variable t, and t is what we call the parameter. Okay, so that is why they are called parametric equations. It's because we have a third variable that we call our parameter, and it's going to be t. Okay, so you're going to get something that looks like this. X equals a function of t, y equals a function of t, and together they are going to be the set of parametric equations. Okay. As t varies, we are going to get x, y coordinates. So we're going to be able to plug t values in and get an x value, get a y value. Together, they're going to make x, y coordinates. And those coordinates are going to form a curve. And that's what we're going to call a parametric curve. Okay, we're going to graph just like we normally have, but something different is going to happen with that graph because we have these t values that we're plugging in. Okay, so big picture here. Instead of one equation, we have two. And these two equations are going to be in terms of a third variable, t. Okay. Now, what's going to happen with our graphs? Okay, here I have two graphs for you. Okay, and I'm going to back up really quickly. We are used to something we call rectangular equations. Okay, rectangular just means the xy coordinate, and we move rectangularly. So I mean, we kind of move in squares, but rectangular squares, it's just a special kind of rectangle. Okay, but when you see the word rectangular in terms of an equation, it just means the graphs that you're used to doing, okay, on the xy plane. Okay, so here our rectangular equation is just a parabola, something that you've graphed for many years in your mathematical careers. Okay, now over here we have a parametric graph. Okay, notice how we have two equations, both in terms of t. So x equals t plus 3, y equals t plus 6, the quantity squared, plus 1. Okay, so I want you to look at these graphs and notice a difference. Okay, in the rectangular equation, we have these arrows up here at the top that signify that our parabola goes on in the vertical direction positively. Okay, now over here, we have arrows along the entire curve. And notice that was a plural arrows. Okay, with our parametric curves, we are going to need to indicate what we call the orientation of the curve. So as we plug t values in to our set of equations, we're going to get coordinates. And as t gets bigger, our curve is going to have a direction. Okay, and I'll show you what that looks like here in our first example. But the biggest difference that we need to see from a parametric equation to a rectangular equation is that there are arrows indicating orientation with our parametric curve. Okay. So let's go ahead and look at our first example. So we're going to sketch a curve where x equals t squared minus 4, y equals t plus 2, and it's going to go ahead and give us the fact that t is going to go from -2 to 3. Okay, and here are the things that I'm going to ask you to do. Okay, first let's figure out what coordinates we're working with. So we're used to making like an XY chart, you know, back like in Algebra 1, Algebra 2 when you graphed. Well, now I want you to think of just adding that third variable in. We're going to make a t XY chart. Okay, we're going to plot these points, and then using that information, we're going to put in the arrows to indicate our orientation. Okay, so let's go ahead and make a t x y chart. And we know that they want the t values to go from -2 to 3. So I'm going to say -2, -1, 0, 1, 2, 3. Okay. Now what we need to do is we need to take our t coordinates and we need to plug them in up here for the x and the y equation separately. So if we take t equals -2, if I plug that in for x equals t squared minus 4, we would get t squared minus 4 is 0. Okay. If we take -2 and we plug it in for t in the y equation, t over 2 would give us -1. And we're just going to do that over and over. If t equals -1, then x equals t squared minus 4 would give us the value of -3. If t equals -1, then y equals t over 2 would give us -1/2. If t equals 0, x equals t squared minus 4 would give us -4. And if t equals 0, y equals t over 2 would give us 0. Okay, I'm going to write down the rest of these coordinates. I want you to work on them on your paper, plugging 1, 2, and 3 in for t, and I'll go ahead and write them along with you, but I'm just not going to say anything, okay? Okay, so here are the rest of my coordinates. And what we're going to do is we are going to plot these in order as the t's progress from smallest to biggest. Okay, so when t equals -2, we have the coordinate 0, -1. Then we move to the coordinate -3, -1/2. Well, it's not going to be perfect. There we go. Then we progress to -4, 0. Then we have -3, 1/2. Then we have 0, 1. Then we have 5, 3/2. Yeah, that's a little better. Okay, so what we're going to do is we're going to actually connect those coordinates in the order that we plotted them. So I plotted them in order based on our t-chart, and I'm going to connect them in that same order. It looks like we have kind of a parabola shape here, nice and smooth. And then using the direction in which I drew our curve, I'm going to add in those arrows to indicate the direction that that our curve is. Okay. And notice how I'm using the plural arrows. Okay, you need more than one. Since this particular problem gave us a range for t, like it started and stopped, so will our curve. Okay, we're not going to have arrows in leading off of that. Okay, there's a starting and a stopping point. Okay. Now, in this particular problem, they gave us the domain. T is -2 to 3. Okay. Well, what were to happen if they didn't give us that stipulation? How would we know what the graph was supposed to look like? Okay. So let's look at our second example. Okay. X equals radical t and y equals t plus 2. Okay. Now, before we just start throwing in random numbers, let's think about this a little bit. Okay. What do we know about radicals? Okay. We know that we cannot have negatives under our radicals. And since that is the case, that we have radical t for our x equation, then we know we cannot plug in negative values for t, because then that would create a negative under our radical. So we know that our domain for this equation is t is greater than or equal to 0. Okay, so for our t xy chart, we know that we can start at 0 because we can have the square root of 0, but then we would need to get bigger with our t values. Okay, so let's go ahead and plug these values in and see what we get. I'm going to focus on one column at a time. So my x column, we have the square root of t. So the square root of t, 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 the square root of t. Our y equals t plus 2. So I'm going to take t plus 2, t plus 2, t plus 2, t plus 2, t plus 2. Okay. Now we can go ahead and plot these points in the order in which we found them. So first 0, 2, then the coordinate 1, 3. Now I'm not really excited about trying to plot the coordinate radical 2, 4 and radical 3, 5. So I think I'm just going to know that they're there, but go ahead and graph my nice point 2, 6, and I can kind of tell what's happening, right? It's like we have half of a parabola. So I'm going to go ahead and connect these in that order, understanding that this is going to go on forever towards the right. We have that orientation where we started at 0, 2, then we went to 1, 3, then we went to 2, 6. So I have multiple arrows indicating the direction of this curve. Our domain was restricted, so I have a starting point, but then it is going to go on forever, and so I don't have a stopping point. So whether it looks like this or you have your curve and your arrow with it, it's not going to be a big deal as long as there's not a coordinate saying that it stops. It does need to keep on going. Okay. Now, some of you may be thinking, okay, this is kind of tedious having to plug in a bunch of numbers. What if we didn't have that domain restriction? How would we know where to start with our t values? How would we know what the curve is going to look like? Okay, it could be frustrating. Okay, so plugging in values for t to get xy coordinates really isn't the best way to graph these. Okay, it is one strategy, but it's not going to be the best strategy always, and it's not going to be the most efficient. It can be used, especially when we have like that a restriction like we did here with our first example, okay? But when we are giving no information about the domain, then it's gonna create some challenges for us. So I want to show you a method that we call eliminating the parameter, okay? And what we're gonna do when we eliminate the parameter is we're basically going to take a parametric equation and we're gonna rewrite it as a rectangular equation, okay? We have been graphing rectangular equations all the way back from Algebra 1. So if we can take a set of parametric equations, something we're really not that used to, and make it look like a rectangular equation, graphs we've been graphing for many years, it might help us out, okay? So what you're gonna do is you're gonna solve for t in one equation, either the x or the y, it doesn't matter, always. Sometimes there's gonna be one way that's easier than the other, and we'll look at that. You're then going to take that t and substitute it into the other equation, and then simplify so that it looks like something that you're used to graphing, okay? So it's fairly simple. There's a little bit of algebra, but it's not a lot of intense algebra that maybe you've been used to, okay? The biggest thing is going to be able to simplify so that it looks like something that you're used to graphing, okay? So I'm gonna come back up here and I'm actually going to pretend that we didn't do any of this, okay? Okay, so what we can do is we need to pick one of these to solve for t. And it really is not going to matter in this case which one we pick. What I would suggest is picking one to where you're going to get a very familiar equation, okay? So I can kind of see where this is going, so I'm gonna help us make that decision. I'm gonna go ahead and take the x equation and I am going to solve for t there, okay? So if I solve for t, that means I'm gonna square both sides and I have t equals x squared, all right? So then I'm gonna come to the other equation and plug that in. So we have y equals x squared plus 2. And that is something that we're very used to seeing and we're very used to graphing, okay? Now, that didn't take us a lot of work, but there is a little bit more thinking that needs to happen, okay? We do still need to think about the domain of our original parametric equations, okay? So what I'm going to do is we're going to come back and I want to discuss this right here. Now, we know that we cannot have negatives under our radical. Okay, so I want to think about how that would affect our x's. Okay, if we're plugging in values where t is greater than or equal to 0, how is that going to affect this x right here? Okay, well, our square root of t's are also going to have to be positive. So we know that x is greater than or equal to 0. Okay, and we really have to think about how this applies to the parametric curve, the parametric equations, because of this. If I go to graph this and I just focus on this right here, then I would be graphing a parabola that is shifted up 2. Okay. However, we can't plug t values in that are negative, which is going to affect what we get for x. And what we decided is that x needs to be greater than or equal to 0. So we don't have those coordinates anymore. We only have half of our parabola. Okay, now how do we know what the orientation is? Okay, when we eliminate the parameter, we're still going to have to think about what our t coordinates would be, but we don't have to really do a lot of work. We can do some of that in our head. So we can think about, okay, if I plugged in 0, x would be 0, y would be 2. And I know that that's this coordinate right here. If I plug in 1 for t, I know I would be at the coordinate 1, 3. Okay, so I thought about 2 coordinates. That's all you would need to think about so that you could indicate your orientation on your curve. Okay. Let's maybe look at one more example, and then you can begin your homework. Okay, so here's our last example. We have x equals t squared and y equals t minus 1. Okay. So in this case, there's actually only one way we can go about eliminating the parameter. So I'm going to go ahead and show you the way that we shouldn't do. Okay. And it's okay to try something and have to erase and go the other way. Maybe you try to eliminate the parameter with one set of equations and it's not working. And so you want to go back and try something else. That's fine. That's why we do math with erasers. Okay. So if we were to solve for t in the x equation, we would want to square root both sides to get t by itself. But remember, when we square root while solving, we get plus or minus. And I don't think that you want to write an equation with a plus or minus in it. I just really don't think you want that. So instead, we better use the y equation in order to solve for t and eliminate the parameter. So if we do that, we have y plus 1 equals t. Okay, and then if we take that and we throw it into our other one, we have x equals t squared. Okay, well, it is a good thing that we have been graphing parabolas that open in any direction because we know how to graph this parabola. Okay, we know that this parabola has a vertex of 0, -1, and that it is opening to the right. And I'm going to go ahead and use the knowledge of, well, since the coefficient is 1, yes, we could talk about focus and directrix, but we can also think about how the shape of the parabolas that we've been working with is unchanged. Okay. Okay, so here is our sideways parabola. Okay. And then what we need to think about, okay, so first of all, notice how I did not put any arrows. We do not want those arrows right here like we did in our conics chapter. No, no, no. We need arrows indicating the orientation, and they probably should be going the same way. Okay, so we need to think about where we would have some of these coordinates. So let's do this. If I were to plug in t equals 0 is an easy one to think about. X would be 0 and y would be -1. That'd be right there, okay? If I plug in 1, x would be 1, y would be 0. We'd be right there. So it looks like we move in the direction like this. Okay. Now there is one more thing that I do want to show you that your calculators are capable of, and this will help you when you go to Miss Cronky's lesson, okay? But I wanted to let you know that your calculators are capable of the parametric mode, okay? So I am going to share my screen one more time with my calculator. Okay, so what I want you to do is I want you to go to mode, and what you can do is you can go to parametric mode. Okay, and what happens is when you go to y equals, then there's actually x equals and y equals. Okay, so we could punch in the square root of t and the t plus 2, like from our second example. Okay, notice how I am still using this X button, but instead of X's, since we're in parametric mode, it's showing up as T's. So watch this. As we graph it, it's going to draw it in the order of the orientation. Okay, now as you play around with this, you're probably going to realize that it's not giving you your whole curve. If you go to window, it's automatically set for the t to begin at 0 and end at 2 pi. So if you were to graph something like our third example, it would not be showing you everything because t is starting at 0. So as you're playing around with your calculator, you may want to change the window to see all of the curve for problems like number 3. But remember that if you want to go back, so you could change, and I probably, like, if I went to y equals and we put in t squared and we put in t minus 1, notice how it's not the entire graph that we just did. But if I went to window and I said, well, I want you to start at -6 for t, then you would be able to see all of it. Okay, well, let's say that you want your calculator to go back to normal. If I go to zoom standard, it takes the window back to where it normally was. Okay, so well, the only problem here is this t step right here. You don't want that to be 7.5. So if you notice that your curve is like really crazy straight and it should be a curve, you probably want this to be 0.13. Okay, so I think what happened is my calculator is in degree mode. So when I did zoom standard, it went everything in degrees. Notice the 360. Okay, so you'll probably want to make sure you're in radian mode. I didn't do that. But if you're having some trouble with your curve, go to window, and that t step should be something less than 1 so that you get a curve with your values. Okay, so you have some homework, and then you have a lesson from Miss Cronky and another assignment that goes with that. So we will see you next time.